Hello, everybody, and welcome to this webinar regarding the new features in FEM-Design 18. My name is Flavio Popescu. I am a technical sales supporter at Strusoft, and I will be your presenter today. And with me is my colleague, Hanif Lomo, and he will be answering any questions you might have. As today we'll be using this GoToWebinar platform, I will ask you to please write your questions in the questions field in the GoToWebinar window. There's a questions field, and if you type them in there, my colleague Hanif will be able to answer them. I hope that we will be able to answer all of the questions that you might have in the time that we have available. If not, we will come back with a follow-up email where we will address any unanswered questions. Okay, today we're going to look at some of the major new features in FEM-Design 18. There are a lot of new features and new implementations in the new version of FEM-Design 18. If you are already users and have a maintenance, then you should get the update and in help check for update, you can see if you have updated to the latest version FEM-Design 18 or not. Okay, I'm going to start with a very exciting new feature, which is the reinforced concrete shell detail results. This is a feature that has been a request for a long time, and we are able to implement it now in FEM-Design 18. So once you have a shell element, like a concrete shell, and you have reinforcement, and you have designed it. For example, I have my, in this example, I have my reinforced concrete plate here, and I have designed it, and I can see that I'm happy with the utilizations for my layers of reinforcement: bottom X, bottom Y, top X, top Y. Also have some crack width here at the top, but I can now see the detailed results and detailed calculations for this plate now in FEM-Design 18. If I go to results, well, maybe this is a good time to introduce this quick tools, which is also new in FEM-Design. It changes the layout of the program. Those of you who have already upgraded, you have noticed it already. But the quick tools window here, which can also be hidden like that, or undocked from here. We can also dock it back. You will see that the layers are now here: the drawing layers, the object layers, and the layers for the load cases. So it will all be in one window for ease of accessibility. Again, you have the results here as well. So every time you do a calculation, you will have all the available results here, instead of having to open a new window and there are new results here. That is, this is new with this quick tools. Once you change a result, you can select the display options here and click on display to change the view. or you can double click as well. Okay. Having this said, we can now proceed to this feature that I started with, which is the reinforced concrete shell detail results. In these RC shell results, in the RC Design tab, I have now the detail results tool. I select my plate and I can click on any point on the plate and get a detailed report of the calculation that has been performed, design calculation. I have the properties of the concrete, the required reinforcement. I have some design combinations here from the design forces taken from the program. And then I have cross sections of that specific point with the distribution of the stress and the strain. So I can see my compression force, for example, in the concrete, and the tension force in the reinforcement bar. I can also see how the reinforcement has been calculated here according to the Eurocode formulas. And I have also an MN interaction curve here with the red X's signifying the design forces that are being used. So you can click on any point on the plate and have this detailed report available. You get the internal forces, which are taken from the model. You then get design forces, which are calculated based on these internal forces. And for the design forces, 8 design combinations are created with moment and force. This is available for any type of shell. It is also available for walls. Let's see if I can design a wall here, put some reinforcement in it. Then I can do the same thing, go to detailed result, select my wall there, and click on a point, and get the detailed calculations for that point. With the cross sections and MN diagram in the documentation. You can also select several points. So if you go to detailed result here, you can uncheck this display result bar tick box, and then select some points, and then go later and check the results for those points. Just please, if you have questions, I will just repeat that for people who have joined a little bit later. Use the questions section here, and my colleague Hanif will try to answer all of them. If we don't manage to answer all of them live in the presentation, we will come back with an email and address the questions there. Okay, I'm just going to go ahead and proceed to the next feature, which is the concealed bar. The reason for this concealed bar was to give precast producers results in the form of forces in the walls and not just stresses. So the shell results are not affected. It is just another way to show the results through this concealed bar. So what this concealed bar actually is, in the RC Design tab, there is now an extra tool here called Concealed Bar Reinforcement. And this tool is used for converting or handling a strip of wall and handling it as a bar. So in these situations, you want to add reinforcement in these areas here as for a bar instead of a wall, instead of a surface element. So you use this Specify Concealed Bar tool. I think I'm going to need some reference points here to make my life easier. So for example, I use this Concealed Bar tool. I can also choose the local system of the shell or a user-defined direction. Then I choose my wall, and I choose the strip like this. And this strip is now handled as a concealed bar, as we call it. All the results and the reinforcement that will be applied, the design will be as if this were a bar. Okay, so I can just go ahead and I have the same tools as for any concrete element. Since this is our bars, I can also define buckling lengths for my bars. I have calculation parameters for them to set with allowed crack width, maximum distance between calculated sections, and cotangent of theta, according to Eurocode. I also have the check option, where I can check the utilization of my concealed bars. Here in the Results tab, I can see the different new category for these types of results called RC Concealed Bar. And here I can see all the results, internal forces, shear, and moments, and Y and Z. Of course, for this, with the new one that I created, I need to make a design for it. Again, I have auto design and manual design to add reinforcement in it. I can also see the detailed results here. I can see that bar with the reinforcement and the stirrups and the calculations performed. Crack width and a summary there. So this was the concealed bar feature, which is one of the new major features in FEM-Design 18. It can be found in the RC Design tab here. Concealed bar reinforcement. Okay, I'm going to go to the next feature that I want to show, which are actually some improvements to the buckling length. Since we looked at the buckling length of these concealed bars, we can take a look at the buckling length improvements made in FEM-Design 18. The lateral torsional buckling for top and bottom flanges can be calculated now separately. You can also choose easily the same value for both flanges. So after the lateral torsional buckling for the top flange and the bottom flange. The calculation is performed for both flanges independently from each other, the buckling checks. For steel bars, you have the new option to consider the bar continuously restrained by checking this box here. This way, the lateral torsional buckling will be ignored. Another new feature for these buckling, for the buckling length, is the beta factor, which can now be set for all the categories that I want. So if I choose the lateral torsional buckling for bottom flange, I can select my elements and modify the buckling lengths for these specific categories that I want. The beta calculation for flexural buckling is now has now the option to be calculated automatically. So if I just select some of my buckling lengths here, the program will calculate them automatically for me. This beta factor is calculated differently for sway or non-sway members. So you now have the option to also specify if this is a sway or non-sway member in order to get the correct beta factor calculated. There are a lot of new features. Today I'm going to show only the major ones, but you can see all of the new implemented features in our new wiki page. I think you can access that from FEM-Design. And you can see what's new in FEM-Design 18. And here are all the new major features and then other features and improvements. You can see all of them there. I'm going to share this link on GoToWebinar here somewhere, probably in chat. I think it's going to be pretty useful, so you can also read about the new features and see all of the what is new in FEM-Design 18. So I'm going to just share that link in the chat here. Okay, I'm going to move ahead to punching reinforcement improvements. There has been some improvements for the punching reinforcement. For example, you can now calculate the punching for a column which is situated at the edge of two plates. That wasn't possible before in FEM-Design 17, but it is now possible in 18. For that, you have to set a effective depth for the two plates in case you have different thicknesses. If you have different thicknesses, you can also calculate this effective slab depth automatically or specify it manually here in the calculation parameters. Also here, you can set up the K-max, which is according to the updated Eurocode for punching. This K-max value is possible to be edited and has been implemented in the calculation. In the detailed results, there has been some improvements for the edge and corner columns. It is a better representation. It is a better graphic representation of the punching reinforcement, which are now cut at the edge of the slab. That happens both for edge and corner columns. As you can notice here, there are some new types of punching reinforcement. You can see them here in the parameters. There are the stud rails. The stud rails punching reinforcement, which are standard, and pay co-products. These are new punching types of reinforcement. You can set the parameters here. In the manual design here, you can set the geometry of these stud rails. You can choose the display, which can be radial, orthogonal, or semi-orthogonal. And you can set the number of rails and the number of studs on each rail. You can set the distances, and you can see here what these measurements actually mean. So there are some new types of punching reinforcement that you can use, these stud rails. You can see here the different types, as in radial. No, this is radial, orthogonal, and semi-orthogonal. As for punching reinforcement, the detailed results are still available, so you can just right-click on the design punching reinforcement and get a documentation report for all the calculations performed and verification checks. You can also check out the short presentation videos about each feature. They are on YouTube on our official Strusoft channel, and there you can find all these major features shortly presented, together with, of course, all of our training material, which are recorded webinars and courses and tutorials. So that is also a very useful page. I'll share that here as well. before I move to the next feature that I want to present, which is the footfall analysis. This is a completely new analysis engine for footfall analysis and for studying the response of the structural elements under a given excitation. Here in the Loads tab, you have the footfall analysis data. You have three types of excitations that you can perform on an element. You have the self-excitation, the full excitation, and rhythmic crowd load. This third one, the rhythmic crowd load, is actually represented by a load case. So you have to define a load case for it to be considered as an excitation force instead of just using this footfall analysis data. That's why they're a little bit different and not in the same panel here. But I'm going to briefly go through each of them and see how you can use them. The self-excitation, which is the first one, considers a point load in several nodes and calculates the result for those nodes. So there's a point load acting in several nodes, and the results are calculated for those specific nodes. How it works is that I need to define this surface, and in everything that is included in this surface will be considered for the footfall analysis. So I can actually just delete this and maybe do it again. Let's draw a surface like that. So all the nodes intersected by this surface will be considered. This distributor line represents the mass of the structure. And in this case, it is represented as a line load, and as necessary, it has been converted into a mass. It is a load case here, a load case for this line load, and it has been converted to mass with this load mass conversion, as you need a mass to be present, to be available. So I've defined all of these, and then in the analysis calculation, there's a new analysis option called Footfall Analysis. Here I can set up my analysis and choose from the three methods which I've previously named: the self-excitation, full excitation, and rhythmic crowd load. Here I can find parameters, the frequency data, and Fourier coefficients. Here's the Fourier coefficients, which I can also user define them manually or choose them from this concrete table, which I have predefined here. I'll click OK when I'm happy and just perform the analysis. In the results, I will have a new category of results called footfall calculation, and I have some new results: nodal masses, which are the masses in each of the nodes. Then I have a total mass of my structure. I have the vibration shapes, which is a translational displacement and a rotational displacement, acceleration, and response factor. I can also have a detailed result for these values and have them in a graph like this with the frequency and response factor. I can see the graphic representation of steady state and transient response. Similarly, I can define a full excitation. I actually have a separate example for this. I can define a full excitation, which is a point load acting in one. It is a point load acting in one node, and the results will be calculated for all the other nodes in my structure. Again, I have to have some mass defined. This has been converted from a load case, which is this surface load acting on my structure here. And I have to define a full excitation point, which in this case is this center point here, which I have defined earlier. I can also place it wherever I want. And similarly, I can perform an analysis. Check my setup. As you can see, the parameters for the full excitation are similar to the ones for self-excitation. And I can just go ahead and perform this calculation and get similar results as for the self-excitation. The masses for each node, the total mass, and the displacement and response factors. The third excitation method is the rhythmic crowd load. For this type of excitation, I need to have a load case defined. So I have defined some load cases here, which are the structural dead load, some imposed loads, and the crowd load, which will act as my excitation force. Again, I need to have masses. So I have converted my two load cases, which is the structural dead load and the imposed load, and the crowd load will act as my excitation force. I can take a look at how that looks. It could be, for example, in this case, a stage which has a load here, a surface load here. Then in the Analysis tab, I go to Footfall Analysis and Setup, and I can see that the parameters are different for this rhythmic crowd load. I have to specify which load case is considered as the excitation force. And my example is this crowd load. I have to set up the frequency data and the Fourier coefficients. For this type of excitation, I can choose the Danish annex and take the Fourier coefficients from there. Just perform an analysis. And see my results. Again, with the masses and the displacements, translational displacements and rotational displacements, and the response factors. So here you have the three methods for performing a footfall analysis. The last feature that I want to talk about today is the construction stages, which is another major feature implemented in FEM-Design 18. The construction stages allows for the study of the effect of the construction stages on the final structure. In the Structure tab here, you can define some construction stages. You can do that manually or generate them by stories. I've made a simple example here with 2 construction stages in which I add some columns at the end. It is possible to use color coding as well and have the elements be identified as for their specific construction stage. So have different colors for different construction stage to be easily recognized, as in my example here. I can manually assign an element to a specific construction stage using this reassign tool. So I just choose the construction stage and then I choose the element that will go to that construction stage. This is for the structural point of view. Now for the loads, I also have a construction stage here, a construction stage menu, and I can choose the load cases that will be assigned to that specific construction stage. I can also set how these loads will be considered only in this stage, from this stage on, and shifted from the first stage. In the Analysis tab, I have a new calculation option, which is called the construction stage. And you have 2 methods to perform, which is incremental tracking method and ghost structure method. For the incremental tracking method, the structure is analyzed stage by stage. For the ghost structure method, the whole structure is considered, but the stiffness of the elements that are not in that specific construction stage is severely decreased. I'm going to perform a incremental tracking method analysis. Then I can see the displacements and the internal forces for different stages. I can use this dial as well. I can also choose the stages from here. You can see that in this case, the columns that have come in the second construction stage have 0 moment, as these beams were already deflected from the first construction stage. These are the major features that I wanted to present today. It's a lot of information. There's more information, even more information on the document that I've shared with you here, where you can see all the new improvements and features. I'm just going to allow a few more minutes if there are any other questions, which you can type in here. If you don't have FEM-Design installed already, you can go to strusoft.com and apply for a trial at our FEM-Design local page here and click on Get Started Now. Apply for a trial license and fill out the form. And you get a 30-day trial period where you can test the program and some of these new major features. Thank you very much one more time for participating in this webinar. please contact me for further questions or details regarding FEM-Design, some trials, or any other questions regarding the features of FEM-Design 18. This is my email address and telephone number. Thank you one more time, and have a great day.